Okay, for some reason, either because you're curious or you just want more points in your freshman physical science class, you are going to take my centripetal force quiz. Okay, so that's why the quiz is here, and I'm shooting this video because a kid asked me, or told me basically, that the video that I had been using, which was made by somebody else, they didn't like it, and they said, why don't you make your own? So I'm going to give it a whirl here, and we'll see what happens. So before I get into all this other stuff down here, I want to try and describe what centripetal force is. And so I'm going to write a definition. So here's my definition. Centripetal force is the force that makes or keeps something going in a circle. And it doesn't have to be a whole circle, it can just be a curve, like this example with the car here. This car is coming around a curve like this, and centripetal force is what's keeping it moving in a circle. For example, if you could put a bunch of ice or an oil slick or something in front of the car, what would the car do? The car would take off straight in the last direction it was going. But it's the friction of the tires with the road that keeps it going in a circle. So here, it's friction causing the centripetal force. In this case right here, I drew a person's twirling something over their head. This string here provides tension. So in this example, it's tension providing the centripetal force that keeps the object going in a circle. What's the force that keeps the Earth going in a circle around the sun? That force, you probably know, is gravity. So it's kind of hard to see friction, hard to see gravity, but right here, tension, you can see a string. So those are just three examples of centripetal force keeping something going in a circle. What's next? So centripetal force acts on objects. So right here, this rock going around. Right here was the car going around. Here it's the Earth going around. Centrifugal force is something you've probably heard of. For years and years, I never really thought of centrifugal force as real. And the reason why is because if you turned gravity off, the Earth doesn't suddenly take off this way. The Earth would actually go this way. So if the Earth were coming around its orbit right here and you turn gravity off right at this spot, the Earth would go off right here. Just like the car would go off at 90 degrees to the center of this turn right here. That's what the Earth would do. Or if you were swinging something on a string, it's kind of hard the way that I drew this person, but if they were swinging it on a string around this way, it might come flying right out of the screen toward us. So this centrifugal force, the one that counteracts the tension pulling inward, you're pulling inward, that centrifugal force is what pulls outward, but it doesn't act on the object, it just acts in the situation. So that's why we call it a virtual force. I don't think I've done this yet, and I should. If you want to know where the equation comes from for centripetal force, you should really visit Khan Academy and just type in centripetal force. He's got 2 awesome videos that will explain to you where it comes from and how the equation is derived. So what is the equation? Well, it's an extension of, or it's an expression of Newton's second law, F equals ma, except we write these little c's here to remind us we're talking about something going in a circle. And it's, no, the C isn't for circle, it's for centripetal. That means center seeking, but hey, good enough. The actual equation we use for centripetal force looks more like this. Force centripetal equals mass times velocity squared over the radius. So if you've got your math cap on, you're like, oh, so acceleration centripetal is v squared over r. Yes, that is true, but that's not something that a freshman needs to know, in my opinion. So I'm going to make up some numbers about my person twirling this rock on a string here for this equation, and I'll solve it in a second. So I made up some numbers here. I made up a mass of 2 kilograms, a velocity of 4 meters per second, and a radius of 0.5 meters. So the radius is how far away the object is from the center point, that's r. M is mass, v is velocity. So I left the units off here, and I'll get back to that in a second, but if we put in 2 here, 4 here, and a 0.5 there, we wind up on the top with 32, and on the bottom 0.5, so we wind up with 64. 64 what? Well, mass is kilograms, meters per second squared, but we've got meters on the bottom, so one of the meters cancel, so that would be meters per second squared, and that's it. Now we don't usually say this. We usually just say 64 newtons. So it takes 64 newtons to make this rock go around in a circle over this person's head. If you're taking this quiz, you've already passed manipulated equations, so I am not going to go into what do you have to do if you want m by itself, or v, or r by itself. Those are things that you should definitely, by this stage of this class, you should definitely be able to do that on your own. So I'm going to try and finish in 1 more minute. So let's just say an example that I like to give the freshmen is someone's twirling a mass on a spring over their head. So this mass is getting spun around in a circle over this person's head. And they're trying to keep it at a steady velocity, and they're trying to keep it at the same distance. So in other words, everything's static. It's all kind of staying constant. What happens if the person twirls the object faster? If they make the v bigger, if the velocity gets bigger, that makes the equation bigger, right? But what if you don't? I shouldn't say it that way. But if you spin it faster, what's going to happen is you're going to keep pulling toward the center. You're going to have to pull harder. And what's the object going to do? It's going to respond by going outward a little bit from you if you swing it faster, right? That should make some common sense. I don't know. I think I might be entering the point where I'm talking too much in this video, so I'm going to stop it right now.